This is Professor Jeff Wilkerson at Luther College, bringing you an introduction to exercise 11, distances of Cepheid variable stars from astronomers as observers and experimenters, published by Kendall Hunt. This exercise introduces us to the idea of how we find distances in the universe using Cepheid variable stars. And there are a number of learning goals we can associate with this work. You can associate your own learning goals with this work, of course. I like to think about distances to galaxies, distances to stars, but also practice in how we analyze data to getting better at analyzing data to make models of the physical universe. So the Cepheid variable stars are incredibly important steps in the use of Cepheid variable stars to find distances, let's say it that way, is an incredibly important step in the cosmic distance ladder. It's a rung on the cosmic distance ladder. The reasons it's so important, Cepheid variable stars are bright, and so you can see them pretty far away. And the period luminosity relationship of these objects is pretty tight. And so as long as you're careful about the type of Cepheid you're looking at, you have a pretty good period luminosity relationship. And periods are relatively easy to measure compared to other aspects of stars. So that these are pretty good standard candles. These are pretty good distance measurements out to a fair distance in the near universe. It doesn't get us deep into the universe, but we can use this step to then calibrate other techniques to get us deeper into the universe. But it gets us past the Milky Way galaxy and out into nearby galaxies and relatively distant galaxies. So this is an important step and good for us to work with it right here and to practice this. So that's what we're going to do in exercise 11. It's built on the pioneering work of Henrietta Leavitt. And if you have the opportunity to find a book, it's an old book now, published in 2005 by G. Johnson, called Miss Leavitt's Stars. It's a great biography of Henrietta Leavitt and a great story of the work that she did in finding out the period luminosity relationship of Cepheid variable stars. So she was able to deduce that there was this relationship, and so that if you can determine the period of the star, you can determine its absolute magnitude. And if you knew its absolute magnitude, then you could find the distance, right? We use this relationship all the time. Distance is equal to 10 to the m minus m plus 5 over 5. And so that's in parsecs. The distance in parsecs is equal to 10 to the power of apparent magnitude minus absolute magnitude plus 5 over 5. So that we can start to determine the distances to objects. In this project, in this exercise, what you have is a table of data taken from a paper that was published in Astronomy and Astrophysics, adapted from that paper, so massaged just a little bit, to find periods of variable stars in the Large Magellanic Cloud. And so with stars in the Large Magellanic Cloud, we can find the periods and the apparent magnitudes, and we can then use the apparent magnitude and this relationship, actually solve for absolute magnitude, which is done for you in the laboratory exercise right there. We can calculate the absolute magnitudes of these variable stars in the Large Magellanic Cloud because we know the distance to the Large Magellanic Cloud. And so that's great. We can calculate the absolute magnitudes, and we can put these absolute magnitudes in here, and we can develop a magnitude relationship, a relationship that relates absolute magnitude to period. Okay, so if you go and you plot your absolute magnitude and your period on a graph together, I printed these out instead of using an old version in a bound book, but to say you have the absolute magnitude here and the period down here, then you can get a relationship. And if you're doing this by hand, you can make a graph like this by hand on here, and you can sort of draw a smooth curve that best fits the data. There's likely to be some noise in the data, but you draw a smooth curve that best fits the data, and you can use that smooth curve to calibrate out any period, any absolute magnitude like that. And so you can even extrapolate on. It's a little dangerous to extrapolate beyond the data you have. You're interpolating between data points. That's a little bit dangerous. extrapolating beyond data points is more dangerous. But if you need to, you can do it. It's your best guess. Just understand there's a lot of uncertainty in that. So then you've got this data set. I recommend, if you can, go ahead and plotting the data that we have for you there in table 11.1. Go ahead and plotting it on a computer and using a functional fit and try to fit a function. Probably a line's not going to do the job. Polynomial might do the job. Logarithm might do the job. You can try different functions to fit. And what we're doing here by trying different functions, by drawing this smooth curve that best passes through the data points, doing it by hand, or by asking the computer to do a functional fit, and trying different forms of that functional fit just to get something that matches the data really well. What we're doing is we're making what's called an empirical fit. We're not trying to model the universe. We're not trying to say this is the relationship, this is the mathematical relationship that has physical meaning for the period luminosity, the absolute magnitude period relationship for Cepheid variable stars. If we were modelers of Cepheid variable stars, we very well would want to know what the true mathematical form of that is and why what it tells us about the nature of those stars and how we might go on to think about density profiles of those stars or something along those lines. But that's not what we're doing here. We're not trying to understand the physical nature of Cepheid variable stars. We're trying to use these stars as distance indicators in the universe. This is why they appear where they do in the text. They are in the distance, measuring distance in the universe version, a portion of the text, section of the text. And so that's all we're doing. So when we do an empirical fit, it means we're not trying to find absolute meaning that tells us something about the stars. We're just trying to find a fit that matches the data well enough that we can use that function to calculate so you imagine this is going to be period down here and absolute magnitude up here. This fit is going to be absolute magnitude is equal to some function of the period. What that function is, if you do this by hand, then you just read it off the graph, and that's great. There's no problem with that. You'd be a little bit more precise if you find out what that mathematical function is, and you can plug the period that you measure in here and solve for the absolute magnitude that way. So what you do, we're practicing this process of first discovering, as Henrietta Leavitt did, first discovering the period absolute magnitude relationship for these Cepheid variable stars. And that's what we're doing first, and then we're going to practice using it to find distances. So if you look at table 11.2 down here, you've got periods of several Cepheid variable stars and the apparent magnitudes, and then we can calculate the distances. So then we would use them as distance measurers down here. So that's all great. That's what you have right there, and you can do this. You can do this work. Then we take it a step further and to say, let's plot some real data from a real research experiment project that we have going on. And you see that data appears in three tables, 11.3, 11.4, and 11.5. And you've got dates, the day of the observation in this particular data chunk, in this particular run, and the the apparent magnitude, the mean apparent magnitude on that night, that night of data right there. So you can see, as a function of time, you can make a light curve for this variable star, and you can make that light curve in three different eras, three different epochs, right there, and right there. One is in July and August 2010, and then again in August and September of 2011, we have data, and then we have data a couple of years later from August to October of 2013. So you get to make these three light curves, which have time, elapsed time. You can just plot the day, observation day number down there, and you've got the apparent magnitude, small m, and you're doing that 3 times. The data is going to be messy. That's what real data is. But this is actual real data from the research project that I do with students, where we take data every clear night, late February to early October of the same field of view. So we've seen this star a lot of different times. Now, the period of this star, the apparent period of this star, is short enough that we need data on a lot of data in a couple of weeks. So if we can have enough data in a couple of weeks, we can start to see the pattern of the light curve that's there, and we can start to get a sense of what the period might be. It's going to be messy, though, and we probably didn't see it at peak, and you might have to interpolate between points, excuse me, to see where the peaks were and try to get a sense. That'd be a half period from there to there. And you do the same thing here, and you do the same thing here, and you try to get a sense of what the period is in each one of these cases. Now, it's perfectly possible that the period changed a little bit from here to here, and you might not get the same period, or you might find a period, and you want to average those three periods to say, here's my best estimate of the period of this star from 2010 to 2013, measured 3 different times in there. That's probably the best way to go, to find an estimate of what the period is and average those periods together. And then when you have the period, use your work to figure out what the absolute magnitude is, and then use the absolute magnitude to figure out what the distance is. And now there's, so this is real data. You're going to have to do a lot of sort of interpolating and smoothing out noise. Again, you can plot these by hand on a piece of graph paper. You can plot these on the computer. It's probably a good thing if you have a computer available to go ahead and plot them on the computer. And you can ask the computer to try to fit them, but the computer's going to have a really hard time fitting them because it's not some really smooth sine curve that's going to go in there. But you might be able to do it. You might be able to try to fit it if you're in a position to do power spectrum analysis, to say, let's do a Fourier analysis. If those words mean nothing to you, then you might not be in a position to do that. But if they are, if you want to push this project a little bit further and do a power spectrum analysis to try to understand what sine curve periods are going in there, knock yourself out. I think it's a great thing to do. It's just not necessary. It's not the thing most people who are using this textbook are going to do. They're going to draw a smooth curve through there and try to estimate half period from trough to peak. And then there's probably enough data in here. I tried to give you enough data over enough time to say, you can measure at least 2 half periods, or 3 half periods, or 4 half periods over the time this data is covering. We're back to what we talked about before. It's a short enough period that you need to get the data within 20 or data within a month. Let's say within 30 days or 40 days or 50 days. You need to cover enough of this to be able to sense what that shape is. And that's not easy to do because as I stand here and look out my window right now, it's raining. And we last got data, what is today? We last got data 5 days ago. And it doesn't look like we're going to get data anytime in the next 5 days, given the forecast. So we're going to go probably 2 weeks without any data, let alone having 5 or 6 measurements over the course of 2 weeks, or 7 measurements that would allow us to map this. So that within the 20 years that we've been taking data of this star, there's not an enormous number of times we can give you clean data to find out what these periods look like. So that's just part of the struggle of being an astronomer and trying to model the universe. Now, we don't even know for sure this is a Cepheid variable star. We have reasons to believe the period is a reasonable period for a Cepheid variable star. The amplitude is a reasonable amplitude, and the color, above all things, the color is such that we think this star is more consistent with being a Cepheid variable star than any of the other classes of stars. Most of the stars that we see in our field of view, the variable stars, we see a lot of variable stars that are pulsating like this. Most of them are what would be classified as semi-regular stars. There are some irregular stars and just a few of what would be called Mira stars in there. Those stars are all redder than this star. And so that's a clue that this star is definitely something different. And they're all different. And they're all longer period than this star as well. And so this star is a different thing than all of the other pulsating variable stars that we have in our field. So we want to test whether it looks like a Cepheid. So what we're doing in this exercise for you with these data tables that you have there, you do these plots, you find these periods, you estimate what the distance is, and say, okay, if it's a Cepheid variable star, this is the distance that I would get to this star. It may or may not be a Cepheid variable star, so you have to use that conditional clause at the front to say, if this is a Cepheid variable star, this is the distance that I've calculated to that star. And that we can think about, we're looking right toward the center of the galaxy, so we can think about where that places that star in the disk of our galaxy or at the near edge of the bulge of the galaxy or what along there. Now, as with almost everything that you do with the data in these exercises, it's prone to observational bias, it's prone to errors and uncertainties and things that get folded in there. And we know from all of the work that we've done in other exercises, maybe you've done it, maybe you will do it, and that project 3 in particular, at the end of the textbook, we know that distance is the absolute apparent magnitude, this relationship that we have written right here is only valid. It assumes that the only thing that makes a star look fainter is distance. Okay, it makes the apparent magnitude go up the greater the distance, and it's true. The greater the distance does make the apparent magnitude go up. But the intervening dust and gas scatters light out, and that makes it look fainter too. So we will, in terms of observational bias, we will always overestimate the distance doing the distance this way, because the star always looks farther away than it actually is, because you don't add light, you only scatter light out as the light passes through the galaxy to get to us. So there is an observational bias built into doing this, and there are ways to correct that observational bias, or at least trap that observational bias and try to make it less of a problem. Measuring spectra of the stars is what you want to do and how you want to go about that. And interesting fact here, that we've been studying this star for 20 years. We don't have spectra of these stars. Spectra, these are relatively faint stars, all of the stars that we're looking at in this field of view, and it's a dense field of view. And spectra are expensive and a little bit challenging to get for such a dense field of view, but it's certainly on our list of things we wanted to make happen here. But for you, for now, see what you can do about estimating the distance. Understand that you're probably going to overestimate the distance of this star, and then see what you can do about placing it in the galaxy. Where is it relative to the center of the galaxy, or relative to where we are in the disk of the galaxy? I hope you find this exercise interesting. I enjoy it. I find it interesting. I think it's a particularly fun and useful exercise to do. It's one of these things. We don't do it every time that I teach the course, and you can't do them all every time you teach the course. We generally do one lab per week when I teach the course over 14 weeks. And so we got 14 exercises we can do. And we can't do, I've already recorded video introductions at this point to something like 18 or 19 exercises. And so we're unlikely to do all of those 18 or 19 exercises. And we have a couple that we do that aren't in this textbook, where we go into the planetarium and we make measurements on the dome in the planetarium. So and one of the weeks we often do one of the projects at the end, and so that tells us that we're probably going to do 12 exercises or so, 11 or 12 exercises out of the text as we work through your one project. We'll spend a week of lab working on it, 11 or 12 exercises. So we can't do them all. Do I dream about maybe rebuilding the course so it's built around where we do almost all these exercises and we use that as the starting point? Heck yes, I dream about that. And we might do that at some point. We might try to write a textbook around doing that at some point. But that's all stuff for the future. Right now, go out and measure your Cepheid variable stars. Good luck with it. Let me know if you have any questions. You can find me. You can reach me if you Google astronomy at Luther College. You're going to find me all over the place, and you can ask me questions about these exercises. So I hope it goes well for you, and we'll have more for you on other exercises.